will try to understand the Hall effect. What do you mean by Hall effect? First of all, let us understand the definition of the Hall effect. See here, it's a phenomena where when a magnetic field B is applied to a conductor, carry current that right angles to that magnetic field, there sets up an electric field VH perpendicular to both the magnetic field as well as the current. So it's a perpendicular to both magnetic field and the current direction of current. There sets up a Hall voltage that is called the VH here. So overall effect is called the Hall effect. So now here one more diagram again clearly shown with the charges they are separated at one side, negative charges on the other side of the here we have considered a strip of the material having certain thickness and having area of cross section A. Overall area is omega into E here. So when being such a material into the magnetic field, I is a current going through it. So I is perpendicular to B. Now the charges they start accumulating. They are charges drifting towards the edges. One set of charges, if you say the plus charges, on those plus charges they get drift towards one side, and negative charges drift to another side. So there creates a potential from positive to negative charges. That potential is called the VH here. So that is a Hall voltage. You can identify this by Fleming's right hand rule. Okay. So now we have seen that it's a rectangle strip, current I, D is the magnetic field, and we assume the electrons charge here is. So under the magnetic field B, the moving electrons will undergo a deflection. They feel a force of Fe that is equal to B, capital B, small e, and V. So this is a force field experienced by the electron under the magnetic field, and there is a current going through the conductor I. Therefore, that will create another field called the Lorentz field that is given by the Fl is equal to E times EH. Fl is equal to E times EH. So you see that both the forces are acting here. One is with respect to the magnetic field, and the other one with respect to the field due to current through going through conductor. So there are two fields, that is Fl and Fb. Fl is a field due to that is called Lorentz field. Fb is called the field due to the magnetic field. So now how long this distribution of charges starts accumulating towards the edges? How long this will go? When the two balances, when the two forces balances, the whole process it stops now. So that is EH is equal to VEV. From this you can get the expression for VH, that is VH is equal to EH into D. So that is equal to BV. And using the current density expression I equal to J is equal to I by A, where A becomes omega D, therefore J is equal to I by omega D. So now you got the J, this I omega T. J is again, you know that is NeV. Ne represents weather as a charge density, so J is equal to rho V. From this we can get the expression for V, that is equal to 1 by rho omega D. Substituting into the expression for VH, that is we expected, the Hall voltage VH is equal to EH into D, that is equal to BVD for V. So if you simplify, VH becomes BI by rho times omega. This is the expression for Hall voltage. So then I will get the expression Hall coefficient. So you know that Hall coefficient is represented by RH here in our explanation. The Hall voltage, Hall field, EH is directly proportional to the strength of magnetic field and as well as the strength of the current going through this conducting material. So Hall field is directly proportional to J and B. The proportional constant you can take it out as RH, that is called the proportional Hall coefficient, that is given by 1 by rho here in this expression. This is the expression for Hall coefficient. The positive sign on Hall coefficient represents it is the due force, and if you get the RH is equal to negative, you can say that the charge carriers are electrons. So in another expression, that is, we can show that VH, we can show that VH is equal to RH within the brackets di by omega. Coming to its uses, they are used to the Hall effect is used in finding the nature of charges, and the magnitude of the Hall coefficient gives us the number of charge carriers per unit volume. It is used to find the mobility of the charges with respect to electrons and holes, and we can decide whether the material under the experiment investigation is a metal, an insulator, or a semiconductor. This is possible. Okay.